All right, where we left off, we were talking about the electron configurations of cations. So let's do the electron configurations of anions. And remember, with anions, we add electrons to the highest energy orbital. All right, so let's look at the neutral configuration for chlorine. And it will be neon is the core, and we'll have 3s2, 3p5. Okay, so my highest energy orbital is my p5. So chlorine minus, I'm going to add an electron to that highest energy orbital. So it'll come out 3s2, 3p6. Or the same electron configuration as argon. So let's take a look at another example, nitrogen. All right, the neutral hydrogen is helium, 2s2, 2p3. All right, so if I make that N minus, I'm going to add to my highest orbital. So 2s2, 2p4. 2 minus 2s2, 2p5. Why am I keep writing the wrong number? 2p5. Right, and we know that nitrogen normally forms a 3 minus ion. So when I get to 3 minus, I'm at 2p6, which is the same as neon. Right, now with transition metals, okay, we're essentially doing the same thing. Remember, our highest energy orbital has the highest N value. Right, so we're going to pull from the highest N value first. All right, so when the N values are the same, like with neon, right, as I get to larger orbitals, as long as my N value is the same, the larger orbitals have more energy. But if I have different N values, my highest N has the highest energy. I'd say let's look at an example of vanadium, which makes wonderful colors of green when vanadium is in minerals. All right, so our neutral vanadium, 4s2, 3d3. All right, so when I go to make this vanadium plus, I'm going to pull from my highest N value first. So this will become argon 4s1, 3d3. And if I go to vanadium 2 plus, then it takes away that last 4s and just becomes 3d3. And now that I have no higher N values, as I continue to remove electrons, then they just come out of that 3D. And vanadium 5 plus will just be argon. All right, so we're always pulling from the highest energy value. The trick is with transition metals, because we have two different N values, the higher N value is still the highest energy orbital. Okay, so I'm still pulling from that highest energy orbital. It just isn't the one at the end of the list. Right, so that brings us this idea, this concept of electron configurations of ions, brings us to the concept of isoelectronic species. Okay, iso means same. Right, so same electron configurations. Right, so our electron configuration for neon, 1s2, 2s2, 2p6. My electron configuration for sodium plus, 1s2, 2s2, 2p6. Right, so same as neon. Right, so sodium plus is isoelectronic to neon. Right, so fluorine, 1s2, 2s2, 2p5. Fluorine minus is 2p6. Isoelectronic to neon. Right, so by that same reasoning, fluorine minus is isoelectronic to sodium plus. Okay, they both have the same electron configurations. They're both the same as neon. Right, so they are the same as each other. Right, so that pretty much does it for our discussions on electron configurations. So now we want to switch gears a little bit, and we're going to talk about atomic size. Okay, and specifically we're talking about radius. Okay, radius of atoms. Right, and there are several different ways that we can talk about that. We can talk about covalent bonds, which share electrons. Right, so in a covalent bonding situation, I'll have atom number 1, and then atom number 2 kind of blends over the edges. Right, so I'm going to measure from the center of each. I have a distance L, so 1/2 L equals a covalent radius. Right, we can talk about metallic. Right, so with metallic bonds, our elements stack up right next to each other. So 2 sodium atoms, for example. And we'll measure from the center of each. So 1/2 L again is our metallic radius. Right, and then we can have ionic radius. Right, so in an ionic bond, you'll have a metal, and your nonmetal is typically much larger. And so we can measure simply the distance between one and the other. So L is our ionic radius. right? So how can we tell the difference? How can size be predicted? Okay, quantum theory of orbitals. Right, so we know that a higher n value means that an electron is farther away from the nucleus. So atomic radii, or atomic radius, is determined by the outside orbital. Okay, the outside orbital, the biggest orbital, and it's related to the valence electrons. Right, so a bigger valence orbital gives us a bigger atom. All right, so let's get into talking about how and why we understand how atomic radii work. Okay, so we're going to use, for a visual, we're going to use what are called radial density plots. Right, and so what this looks like is a graph where on the y-axis I'll have the percent probability of finding an electron at a particular distance. And then my x-axis will be distance from the nucleus. Okay, so if I want to look at what a radial density plot looks like for a hydrogen atom, it looks like a simple bell curve. All right, so this is a hydrogen with a 1s orbital, 1s1. All right, and so the most likely location, so remember my y-axis is probability that I will find an electron at a particular distance, sits at what we call 1 A0, and we talked about A0, that's a Bohr radii. Okay, so at about 53 picometers. Okay, it's the most likely distance from the nucleus that you'll find an electron for a hydrogen atom. Right? Now, if I do the same thing and I look at the 1s for magnesium, let me pick a different color. All right, so this is the magnesium 1s. Right? Much, much smaller. Right? So magnesium has a lot more electrons. Why is the magnesium 1s smaller than a hydrogen 1s? You would think that they might be the same size because they're both 1s orbitals. And the answer is shielding. All right? So magnesium has a Z of 12. And remember, Z is the atomic number. Right? So 12 protons in a magnesium. Right? So the higher Z value has a greater pull on the inner electrons. right? Lots more protons pulling in on those inner electrons. But here's an important thing, is that the inner electrons shield the outer electrons. From the pull of the nucleus. Okay, remember, positives and negatives attract. So positive protons are pulling in on negatively charged electrons. So those inside electrons, the ones that are closer to the nucleus, feel that attraction very strongly and get pulled closer to the nucleus. The outside electrons, on the other hand, are being blocked by those inner electrons. So they don't feel that attraction quite as keenly, right? So the greater your shielding, the farther away your outer electrons can get, and you get a bigger atom. So we're going to stop this video right here, and we'll pick it up with more talk about shielding on our next video.